Recording is rolling. It is Wednesday, January 24th. Here's top scientist for simple harmonic motion and waves. So awesome job if you made that list. Simple harmonic motion and waves. Right? Of course, now we're on to optics. We're doing reflection, refraction type stuff. Club photos. So Friday, today's Wednesday, so we're talking about 2 days from now. So not tomorrow, but the next day. It's a photo day. I got this whole list of clubs and photo times. I did post this to Google Classroom, so this is on Google Classroom. We're kicking off with senior panoramic. It's going to be first period on Friday. So if you're a senior, you at least got that picture, right? They got some time allocated for that. And then if you're in any club, again, this whole list is posted to Google Classroom, so you can see clubs and times. It's all here. Right? All right. So today we're going to focus on refraction, and Snell's law is the math behind refraction. And then, we'll do a lab activity. Well, okay, yeah. It's going to be a kind of a teacher-guided lab. We've just got so many materials to work with here, right? Here's my poster for Snell's law, but really any of the posters that deal with refraction, right? Refraction is light bending through some material. So this glass prism, you can definitely see like any light that's going through it is like bending, right? Or this one we're going to use later, or we're going to have up here. One of my posters have labeled a magnifying glass that is like a converging lens, right? So something to do with light bending, right? You can get these effects, right? So what's that about? Huh? Let's switch over, do some demos. I got a couple of Paul Hewitts lined up. All right. All right. I meant to show you guys some other versions of this too, right? So Isaac Newton did this way back in the 17th century. Right? Holds this prism up to white light, like sunlight, and realizes that the colors spread out, right? So there's refraction. Refraction is the physical term for light bending, right? It bends and refracts, right? But each of these wavelengths refracts at a little bit different angle, right? So the red refracts the least, and the violet refracts the most, right? For the visible spectrum, right? So you got like that, right? It's refraction. So what else we got here? Oh, if you put a straw in water, right? It looks like it's bent. It's not really. It's some kind of optical illusion. It has something to do with light going through it and bending. And ooh, how about this one? Ooh, animation. Ooh, oh, look, the direction of the arrow change. Refraction. Yeah. Right. So got another polyhue tube. I'm going to switch my screen over and more or less draw what he just drew, right, but add a little bit more detail to it. Right? So let's look at what he was just saying here. This might be good for your notes. Right? Suppose you got this line divides two different media. Let's say this is air and this is water. So air versus water, for example. Something like that. Okay. Now, light travels at different speeds through different substances. This whole thing about the speed of light being 3 × 10⁸ meters per second, that's really only true in a vacuum. Through the air, it's almost true. But water, it'll slow down significantly, and that causes it to refract. Why? What's that about? Okay. So let's follow one ray of light. Okay. Say this ray of light comes in, this type direction. Right? It's coming in like, right? Right. Now, we're going to be measuring some angles with respect to a normal line. When I say normal, I mean perpendicular to this surface exchange between the air and the water. So let me get a normal line. So I'm going to mark out 90 degrees. Boink, there's 90 degrees right there. Get a normal line, a perpendicular line. That's what normal is, perpendicular. Okay, so we're going to measure. This right here could be called what's called the angle of incidence, or just like the angle on the side of the air. Okay. Notice I'm measuring with respect to that normal line. Right? Right. Now, what about when that light enters the water? What happens? Right. Let's do what Paul Hewitt did. Look at these wave fronts. Try to make these about perpendicular to this initial line that I drew. Right. So it could be like a wave front. I'll try to get these more or less evenly spaced. A bunch of wave fronts, pretty much evenly spaced. Okay. And maybe these represent like the crests of a transverse wave. Right. Oh, I guess they would continue this way too. So about like this. Right. So we got like crest, 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 crest. All right, so, okay. So, okay, so we're looking at here's crest to crest could be the wavelength. I'll call it lambda, right? Maybe we'll throw a little subscript like 1 for the side of the air, right? Because we're about to see a change, right? Right. Now, did you guys remember a wave formula that goes speed equals wavelength times frequency? You guys remember that one from last couple weeks? Right, speed equals wavelength times frequency. Okay. Okay, now, I said that light is going to slow down inside the water, and that's going to kickstart this whole process. We get a decreasing speed, right? The speed of light in air is pretty close to what it is in vacuum, maybe like 3 × 10⁸ meters per second. Right? But the water is going to go slower. Right? Talk about that later. Right? Right? So if the left side of this equation decreases, well, something on the right side is also going to be forced to decrease, right? Maybe one or both of these, right? But let's look at this frequency for a moment. It's frequency. Frequency. Aren't we talking about like the frequency of, say, like wave crests hitting one point? Right? Like if these are wave crests, right? You put your hand here, right? You see these ripples coming along. It could be like blip, 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 blip. Right? There's a certain frequency, and I'll mark out these wave crests leaving the air. There's a certain frequency of these wave crests leaving the air. Right? So it goes blip, 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 blip. Right? And there's also a certain frequency of wave crest entering the water. But hold on, doesn't it have to be the same thing? The frequency of leaving the air and the frequency of entering the water has to be the same thing, right? So this frequency stays the same, right? On both sides, right? On the side of the air and on the side of the water, right? So going from the air to the water, the speed's going to decrease. The frequency has to stay the same. What does that tell you has to happen to the wavelength? Must also decrease. With the exact same proportion, the speed decreases. Right? Right, so the way you do that is to make these waves bend. And there's your refraction. And when I go label the wavelength, you'll definitely see it. Right. So here's crest, 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 crest. Got a new wave fronts. Right. And here is the crest to crest distance. I'll call that lambda also, maybe like lambda 2. Right. And if you compare those wavelengths, you guys see this one shorter. So that would be consistent. So now we got equal frequencies, right? Frequency of leaving the air matches the frequency entering the water, right? And a decreased wavelength that goes hand in hand with a decreased speed, right? And then if you draw a ray that's perpendicular to those new wave crests, right? Looks like that, right? And there's the refraction. There's the refraction. Right? Right. And then now we got a couple angles that we can compare. Maybe this theta on the side of the air and this theta on the side of the water. Right? Like theta 1, theta 2, something like that. Okay. I'm going to throw a couple other formulas on this page, right, while you guys are taking notes on this. Right? One is something called index of refraction, and that is the speed of light through a vacuum compared to the speed of light inside that particular medium. Okay. Let me go ahead and write that up. I think this is also on. Okay. Okay. Well, I wrote this formula out here, but let me go and label it for the notes. Right. This is called index of refraction. This is speed. C, of course, is the speed of light in a vacuum. And V, I'll give you some other speed. So that could be the speed of light in, I'll say some medium, right? Like water or glass, right? Something like that. You see the light bending, right? Just like that. Okay, so we got this formula here. Speed equals wavelength times frequency. We got this one. Index of refraction is speed of light in a vacuum compared to speed of light inside the medium. Right? Which, by the way, this fraction, does this fraction always have to be less than 1 or greater than 1? What would make sense? Greater than 1. Yeah, the speed of light in a vacuum is always going to beat the speed of light inside, say, like glass. Right? So I can tell you, N for water is like 1.33. Right? Ooh, okay. So like light slows down by some percentage when it enters water. Right? Okay. And third formula I got to throw on here is Snell's law. I'll write that out. Snell's law. Right? Snell's law is going to relate these angles to this index of refraction. Or I guess 2 indices of refraction. This N for air, I'm just going to call 1.0. Right? With a vacuum would be exactly 1. Air is extremely close to that, so let's call it that. So it goes index of refraction times the sine of the angle on that side is equal to the other index of refraction. Oops, that's supposed to be an N2 times sine theta 2. Right? I've got a poster for that too. That's the poster with the pencil on it. Stick pencil water. Right? Okay, so for air, it's 1, so maybe that could be like 1.0. This theta could be so many degrees. You measure that with the protractor. Right? Now on the other side, you got index of refraction of some material. Say it's water, could be 1.33, right? And then you got this angle here, right? It goes hand in hand. So okay, so if you can identify any 3 of these, then you can solve for the 4th, right? Like if you break out a protractor and you get what are these angles, you could calculate what is the index of refraction of this material. That's actually one of the things we're going to do with the lab later today, right? I'm going to have you guys figure out what is the index of refraction of this glass piece right here. What's the index of refraction, right? Or if you know what the index of refraction is, you can predict what the angles are going to be. So you can say, oh, I can predict if I put the straw in the water, it's going to look exactly like blah, 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 right? Okay. And then that could help you too do things like why would you have to know how much light bends for like some material, right? Well, if you're wearing like eyeglasses or we use magnifying glass or build a refractive lens telescope, right? Like this magnifying glass works because of refraction, right? Like here, let me give you guys an example. Right now, there's different kind of glass. Let's suppose I'm just gonna make something up. Suppose the index of refraction of this glass right here was 1.33. It probably isn't, but it could be kind of close to that. Let's call it 1.33, right? So that it would match index of refraction of water. Right? What if you take this magnifying glass down to the bottom of the pool, and let's say you're trying to magnify the bottom of the pool, like yes, look at the bottom of the pool. Would this even magnify? Would this even work as a magnifying glass underneath the water? No, because the indices of refraction would be the same, 1.33 and 1.33 for the glass and for the water. And so these angles would be the same. So there would be no refraction. It would be like as if this was clear, right? That's actually a tool too. I used to do a forensic science class. That was a tool that forensic scientists can use. Is supposed to get some little tiny glass shard from some crime scene. You're like, we got to match this glass. There's different kinds of glass. We don't know where this came from. What's the source, right? So they can take a little glass shard. They can put it in things like some oil or something, they change the temperature, change the index of refraction until it's a match. When it's a match, it's completely invisible. And say, okay, well, now we know for sure that has an index of refraction of like 1.43 or something, right? And they can know where the source of the glass, and that can help them like solve crimes like that. All right. Oh, yeah. All right, so do you guys remember yesterday? I know this week we're focusing on like optics and light, but you guys remember yesterday those whispering dishes was like an acoustic example of reflection. Yesterday we focused all on reflection, right? So let me flip back over to Paul Hewitt. He's got a refraction example for sound. So let's do acoustic refraction. And this will be the one acoustic example you guys will see today for refraction. Yeah, refraction. All right. All right, so what we're about to do in class, it's pretty much this video, but see video version, the in-class version. Here. All right. Yeah, I was gonna do like a full like a lab, give you guys a bunch of materials to do this too, but yeah, realized this morning a little short on materials and our lasers are kind of weak, so I'm just gonna kind of guide you guys through this one, right? But we'll do this too, right? Notice he's got he's got this like protractor pre-set up. He's got this half circle glass piece, right? Which is a really good shape to have because right, notice how the setup. You guys see this normal line, and it's labeled normal. Look at that, normal, right? As in perpendicular. That's what that means, right? So he could have written perpendicular. So normal line, okay? Right. It's perpendicular to the surface between the glass and the air, right? Now, if we were to measure angles, we could measure this angle here and this angle here. So this could be called angle of incidence and angle of refraction, something like that, right? And get into the shape, this half circle shape. Right? The advantage of the shape is as long as you aim this light beam right at what would be the center of the circle, right? Then it'll refract here on the flat side. Okay, so we got some refraction going on. But now any light that emerges from, like the center of a circle, it goes to the outside of a circle, it's always going to be perpendicular to this curved surface. Therefore, it doesn't double refract, right? So, and you can kind of see like through this glass, you guys can see that light beam on the opposite side on the paper. Okay. And then when it emerges on the other side, it matches that protractor on the paper, right? And then that angle stays the same almost, right? Right. And you guys can see that this incident angle inside of the air is growing faster than this refracted angle. Right? You guys see that? Right. So right now it's at 55 degrees on this side, but only what's that 30 something degrees on the side. Okay. So get a phone call. Let me pause this. Pause recording. All right, recording back. Here we go. All right. Now something else you see is, do you guys see this reflection? You guys see some reflection? All right. Now if I rewind the video, right at the very beginning, like I really don't see any reflection there, right? And then it shows up. It's like real weak. You can like barely see a little bit, right? But it's almost all refraction. If you go back to where we were, then okay, now the reflection is getting stronger, and the refraction is getting weaker, right? Now, you might too think, if you can fast forward in your mind a bit, think, this angle of incidence is getting closer to this 90 degrees, and this refracted angle is not growing as fast. I bet it's kind of running. I bet this refracted angle is kind of like running to some limit. You guys think, right? Like here, if you were like an ant crawling around at the 70-degree mark, right? Do you guys think this guy could ever shine the light where it could ever shine directly on this ant at 70 degrees? No, it's never quite going to get there, right? Let's see where it peters out, because he's getting real close, right? We're getting right near the limit. Like this incident angle can only ever go up to 90 degrees theoretically. Right now it's at 80. I think this video stops at like 85 degrees. So we'll let it go to 85 degrees and say, okay, right. There it is. There's 85-degree angle of incidence relative to that normal line, right? And now it's almost all reflection, and there's a tiny bit of refraction, right? It's really weak. And you can see it. It looks like it just went just beyond 40 degrees, maybe about 42 degrees. Does that look about 42 degrees, you guys think? Right there, right? That 42-degree angle has a name. It's called the critical angle. The critical angle, right? And if we look at this in reverse, like what if you shine the light in on the curvy side? And that's the next video I have queued up. All he's gonna do is just same setup, except you just turn it around. So now, look, he's shining it on the curvy side. Look at that, right? Well, now you see the opposite. Oh, look at that. Now this incident angle on the side of the glass is growing not as fast as this refracted angle on the side of the air, right? And he can only go to about 42 degrees, and then right. It's getting close, getting close, getting close. Oh, I see some reflection building up, and ow, right there. Okay, so pause it right when this refraction went like flush with the surface and then disappeared, right? And at that point, it's called total internal reflection. Anything beyond that angle is, right? And what is this angle right here? This is the critical angle. Hey, look, it's the same 42 degrees, just on the other side. You guys see that? Critical angle is 42 degrees. Now, the fact that critical angle is 42 degrees is related to the particular index of refraction of that glass, right? Compared to the air, right? So some index of refraction of that glass piece that would correspond to, right? All right, so switch back over to this projection, right? I think this is the same glass piece because I was trying this last class and it looked like the angles were pretty much matching what was on the video, right? So we'll try this here. You guys got a half page in front of you? Right, we're going to do some investigation. I want to know, what is the index of refraction of this glass piece? What is the critical angle that we associated with that? First, if you know one, you can calculate the other to go hand in hand. But we're about to do all that right here. Okay, you guys got this half page? Right, go ahead and write your name. Right, name. So when I have you guys trying to send by the end of class, who to give the points to? Let's call this Snell's Law Lab. Snell's Law Lab. if you want a poster to keep track of, you guys see the poster hanging in front of my room that has a pencil on it? It says Snell's Law, right? And so, quick review. The green box down here says index of refraction, ratio of speeds of light. Right? And then here's Snell's Law, right? N1 sine theta 1 equals N2 sine theta 2. N1, N2, theta 1, theta 2. Okay, so you guys see how this can connect. Okay. So if we can identify 3 of those 4 variables, then we can solve for the 4th. That's about what we'll be doing. Okay. Make a, while I'm on this page, let's do a table. So what is theta on the side of the air versus theta on the side of the glass, right? We'll take the index of refraction of air to be exactly 1. That's extremely close to. I'll do 3 different sets of measurements, and then here's going to be the questions. Right. We're going to answer 2 questions. I'll have you guys answer 2 questions. Question 1, what is the index of refraction, say, of the glass, right? So what is the index of refraction of this glass, right? So like, how much does light slow down in this glass compared to, say, air or vacuum? And question 2 is, what is the critical angle? Which, I guess, 2 approaches you could do to answer that. One is that we could get it empirically. I'm just gonna shine laser lights through, or we could get that empirically, right? From the video, I mean, this is the same as the video. What do you guys think the answer to that second question is probably going to be? 42 degrees, right? It's probably the answer to that one, right? Or if we solve the first question first, get index of refraction, I bet you could calculate what it would be ideally. Here, maybe we'll try that too and see how close to 42 degrees it is, right? So right, here's where I'm just gonna do this part. And initial plan was to have you guys do this too, but I've only got a few lasers and they're kind of running out of battery, so I'll handle this. Right, show you guys what I do. Okay. So as make believe you're following along with me here. So I got this glass piece. Now I need a normal line. I need to go through exactly the center and be exactly perpendicular to the surface. So here, how do I find the center? Hold this ruler up here. This looks like is that 9.3 centimeters, I think, 9.3 centimeters wide. So what's the halfway mark? That's 9.3 centimeters divided by 2 is 4.65 centimeters. So go over to 4.65 centimeters. Bam! There's the dead center of that piece. Right? And I need 90 degrees for a normal line. So put the node of the protractor right there. Zero out the bottom line, and then go up to 90 degrees. Bam! Then dash that off. Dash. Okay. There's the normal line. Okay. That's the line that I'm going to measure angles with respect to, and I'll always aim the laser like right at this center point there. So get the glass prism back in place. Okay. And I'll try 3 different pairs of angles. Okay. So I got all different colored pens here. How about let's start with the pink ink? How about that? Use this to map this out. Okay. See if I can get this laser to work. So that's in place. It's like I don't know, it's kind of weak. Okay, maybe I can get this one to work. Okay. Okay. So can you guys see that? Is that showing up? Oh, it's not even showing up there. Okay. Is it showing up on the video? Let's see if this shows up on the video. Oh, that's a good idea. Turn the lights off. Yeah, thank you. I like that suggestion. Let's do that. So it shows up any better. Oh, that I think that did work. That does work better. Good call. All right. So let's see if I aim this at like this direction, straight for the center. Right. It's coming in like this angle right here. Okay, right. And that angle. Okay. Let's see, where's that refract out? Where's all right, last class I know I saw a red dot show up on it. Oh, okay, I can kind of see it. See it right there. Okay. It's really hard to tell. Also, I'm looking through it. There's refraction, which might mess it up too. But okay, it'd be right about there. I don't know if this is going to be 100% accurate, but probably be close enough. Okay. So there's incidence, and there's refraction. Boom. Good. That's pretty close. Okay. And so let's grab these angles. I'm looking at what is this angle here? Theta on the side of the air compared to this angle right here, theta on the side of the glass. Okay. So take protractor, park the node right there, zero out the normal line. Right? And it sweeps through. Looks like 38 degrees. So on the side of the air, I'll call this 38 degrees. Right? And let's see, flip my protractor, zero out that normal line again. And that sweeps through 24 degrees. 24 degrees. Right? That's one pair of angles. You could probably solve these questions with just that, but I'm going to do another couple of angles just for practice. Yeah, so 38 and 24 degrees. Right. Right. Prism back in place here. Right. How about this type angle? Right, let's do some green ink with that. Just green ink. Right. And then, right, where's this red dot on the other side? Ooh, I see it. I see it. It's like right about there. Okay. Okay, so now what is this angle compared to this angle? Right. Right, so, oh, whoops, no, I'm being silly. Right. Relative to that normal line. Oops, oops, oops. Okay, that angle compared to this angle. That's right. Okay, so normal line, zero out. Okay, it's gonna sweep through 58 degrees. So 58 degrees. Okay. Then on the side of the glass, it's gonna be 32 degrees. 32 degrees. Right? Right. Let's do just one more. This is a fun lab to do with the triangle too. The triangle, it would refract twice, right? From the air to glass and glass back to the air. So that could be an extra fun setup. Right. Right. How about purple ink? Right. And purple laser. Do a pretty steep angle here. Come in at this angle. Okay, I see a red dot right there. Bam. So now I'm doing this whole angle right here compared to this angle right here. Right? So what are those angles? Right, so the angle on the side of the air is showing me 71 degrees. 71 degrees. And on the side of the glass, looking at 40 degrees. 40 degrees. Okay. 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 All right. I don't know if I was going too fast in my last class or what, but right. Last class I gave them about 5 minutes to try to solve this, but we only have about that much time left in class, so I kind of hate to do this, but I'm gonna go over this with you guys. Right. So solve this with you guys. What is the index of refraction? Index of refraction. Let's say I pick the grade set, just to pick one. Right. So n1 sine theta 1 equals n2 sine theta 2. Right. On the side of the air, I'll call n1 just 1. Right. Sine, right, so 58 degrees, right, equals, right, and let's say we're solving for n of the glass, just what that would be, times sine of, that's 32 degrees. Right. So you guys see n for glass could just be, let's see, 1 times sine of 58 degrees over sine of 32 degrees. So that'd be, right. Let's put that together. What is sine 58 over sine 32? Right. Looking at 1.60. Right. You know what? I can very quickly whip in these other numbers. So 38 compared to 24, 38, 24. I'm getting 1.51. And how about the last pair? 71 and 40. Tells me 1.47. All right. Okay. So 3 pairs of angles, and I'm getting 3 a little bit different values, but look, they all kind of bounce around 1.5, right? A little bit more than, a little bit less than, they're about 1.5. Right. So you guys think the answer to this question is probably like 1.5? Right. Let's call it 1.5. Let's call in glass 1.5. Okay. Now, if in glass is 1.5, the other thing I want to figure out is what is this critical angle? Right. Now I can get this empirically, and you guys saw in the video demo, it was like it looked like 42 degrees. You guys remember it was the limit? Right. Let's run that mathematically. Right. Yeah, I think it's the same glass piece he was using too. Right. Right. So can I go Snell's law, n1 sine theta 1 equals n2 sine theta 2. Right. Right. Well, on the side of the air, we're talking about where the angle goes to 90 degrees. Guys, what is sine of 90 degrees? 1, right? And then glass, we just found, so let's pop that in as 1.5. Sine of theta critical. Let's solve for theta critical. Right, so everything on the left side is just equal to 1, 5 by 1.5. So theta, this would be theta critical, is, so take 1 divided by this 1.5, or in general, the index of refraction of the material, okay? And do an inverse sine of that. Or I could have asked you guys, but we're running a little short on time. How do you extract an angle out of the sine? Well, you take an inverse sine. Right? We've done that before. Right? Done it similar. Right. So let's see. What is inverse sine of 1 over 1.5? Right. Getting theta critical is, oh, look at that. 41.8 degrees. Probably about 42 degrees. 42 degrees right there, isn't it? Yeah, you guys see that? All right, so there's the 2 answers to the question. What's the index of refraction? In glass equals 1.5. What's the critical angle? Theta C equals 42 degrees. Right? Okay, you guys good? Right, so you guys got that. You guys got the table. You guys got your name. Throw that in the great tray. Come lights. All right. You guys have a good day, and I'll see you tomorrow.